Basics in Metallurgy of Nickel Titanium Endodontic Rotary File. In 1960, nickel titanium alloy was developed by Buehler. Nitinol stands for Nickel Titanium Naval Ordnance Laboratory. So what is a special feature of this nickel titanium? This nickel titanium can withstand about 8% of strain when compared to that of the 1% of other alloy. So it can withstand more strain. So it has two important properties. It has shape memory and superelasticity. These are the two important properties. So what is the composition? Nickel titanium, right? Nickel is 56% weight and titanium is 44% weight. So they both are in the equiatomic ratios. 2% of nickel can be substituted by cobalt. Let me discuss about the importance of cobalt substitution later. This is the most important part to understand the basics behind the metallurgy of nickel titanium endodontic alloy. So this alloy during higher temperature ranges will be in austenite phase. So when we cool it through the critical transformation temperature range, it turns to martensite phase. So when we are going to heat it, reverse critical transformation temperature range, it turns back to austenite. So in between this, twinned martensite, when it is deformed, it can turn to detwinned martensite. Okay, so austenite, twinned martensite and detwinned martensite. So in between this austenite and martensite phase, we have another phase called as R phase. We will discuss about the importance of R phase later. So because of this transformation from austenite phase to martensite phase, the shape memory property becomes possible. So manufacturer can decide at a particular temperature range whether the file to be in austenite phase or the file should be in martensite phase. This can be determined by the manufacturer by educating the nickel titanium alloy to be in a particular phase at a particular temperature. And this property is called as shape memory. So when austenite phase turns to martensite phase, there occurs change in physical property of the alloy also. So this martensite phase is extremely ductile when compared to austenite. Austenite is hard. Now we have seen the reason behind the term super memory. Now let us see why this nickel titanium is super elastic. So what is super elastic? When we give a load, it deforms. When the load is released, it turns back. It springs back to its original position. And this property to nickel titanium alloy is because when the austenite phase is going to be stressed, it can transform into martensite phase. Usually when we stress, slip occurs, but here in nickel titanium, slip does not occur, that is slip plane does not occur. The total atomic movement between adjacent planes of atom is less than a full interatomic distance, and this is the reason why our nickel titanium alloy shows the superelastic property. So austenite phase transforms to martensite phase during critical transformation temperature or through stress. So in between these two phases, R phases is there. So importance of R phase. So because of the superelastic nature, initially in conventional files, the files has to be grounded. If we twist the files, they cannot stay for long because of its superelastic property. But in R phase, you can twist the files. So this is the turning point in manufacturing of nickel titanium files where the twisting of files is possible. So let us discuss about the importance of austenite finish temperature. So for this is CM, that is controlled memory files. So austenite finish temperature is 55 degrees centigrade. So what is austenite finish temperature? So austenite finish temperature, the file will be mostly in austenite phase. Then when we start to cool, the martensite start phase begins, and when it is completely transformed into martensite phase, it is called as martensite finish temperature. Then when we start heating, austenite start phase begins and austenite finish occurs when the alloy is in austenite phase. So by the term austenite finish, we can know that the file is entirely in austenite phase. That is, it mostly has austenite phase. So in 55 degrees centigrade, only when the temperature reaches 55 degrees centigrade, the austenite finish will occur for the control memory files. So intracanal temperature is usually less than the body temperature. Let's say around 30 degrees centigrade. So in 30 degrees centigrade, CEM file will not be in austenite finish. That is, the austenite finish transformation will not be complete. Will not be completely in austenite phase. M wire, it is austenite finish phase is 50 degree. So M wire will also not be completely in austenite phase. So if this wire has to be completely in austenite phase, it should reach 50 degree, but the intracanal temperature is only around 30 degrees. It is less than the body temperature. Now let us consider the example of twisted file. Twisted file, austenite finish temperature is 17 degree. In 17 degree itself, the twisted file will mostly have austenite phase. Therefore, in intracanal temperature, this twisted file will be in austenite phase, and most of the conventional file will be in austenite phase. But nowadays, because of heat treatment, we are preferring the files. The newer generation files are mostly in the martensite phase during the intracanal treatment procedure, because the martensite phase is ductile and it has more cyclic fatigue resistance when compared to that of the austenite phase. So this is M wire. Example of M wire is profile vortex and vortex blue. Few example. So in M wire, while we are studying it with the differential scanning calorimetry, we are able to see that it has more austenite phase and some martensite phase. Since austenite phase is still present in larger significant quantity, the superelastic nature is present in M wire. In CM wire, examples of high flex CM and typhoon CM, it has a mixture of austenite phase and martensite phase, but it appears that the martensite phase is more. Therefore, this CM wire has no superelastic property. The next is the R phase. R phase is the rhombohedral phase where the file can be twisted. The example of this phase is TF adaptive. The important point here is many studies have stated that the torsional fatigue resistance of this R phase is actually less. Then austenite phase. In race files, the conventional files where the files will be in austenite phase during the in the intracanal temperature. So importance is of cyclic fatigue and torsional fatigue. So cyclic fatigue occurs when a file rotates freely in a canal in a curvature. What happens when the file rotates within the canal curvature? It undergoes a series of compression tension cycle, and as a result of work hardening, the file fractures. It is cyclic fatigue. And torsional fatigue is when the tip of the file is locked apically and the file continues to rotate. What happens? Torsional fatigue occurs. As the elastic limit of the file is being reached, the torsional fatigue occurs. So cyclic fatigue, M wire, CM wire or any martensite dependent based files have improved cyclic fatigue, and this is the reason why nowadays most of the files are being heat treated and most of them are in martensite phase. I hope this video was easy to follow and I hope you could understand some basics behind the metallurgy. Thank you. Let us also know what is cyclic fatigue and torsional fatigue. Cyclic fatigue occurs as a result of rotation around a curve. by the repeated tension and compression of the metal, finally work hardening followed by fracture. That is, when a file rotates in a canal curvature freely, it undergoes a series of compression tension cycle. As a result of it, what happens? Final work hardening of the metal occurs and followed by fracture. What is torsional fatigue? Torsional fatigue occurs when the tip of the rotating instrument is binded within the canal and the motor continues to rotate. So torsional fatigue occurs when the ultimate strength of the material is exceeded. And that's why each manufacturer gives us a specific torque range and we should work within that, and that's the significance behind it. Let us also know about the importance behind the cobalt substitution for nickel. So by doing a cobalt substitution, we can reduce this critical transformation temperature. Then the heat treatment temperature for the nickel titanium alloy will be in the range of 400 to 600. So when it goes beyond 800, recrystallization occurs, and this is also an important point to know. I hope this video was useful and I hope you were able to follow. Thank you.